Hydrogen is one of the energy sources of the future. Why? It provides clean energy. When generating energy from hydrogen, the only waste product is pure water. There are no pollutants, no particulate matter, and, above all, no CO2. The challenges with hydrogen to date are storage and transportation. Common methods include compressing hydrogen under high pressure, liquefying it at very low temperatures, or chemically converting it. But all these methods require a lot of energy and are complicated. In addition, the storage of large quantities of hydrogen is associated with safety risks, as hydrogen is an extremely flammable gas. To all these challenges, we present a solution that comes from nature. It is a bacterium from Lake Kivu in Africa. Under mild conditions, this bacterium can convert hydrogen into a form that can be easily stored and transported: formic acid. And the best part? This bacterium can do it in both directions. It can store and release hydrogen. And here in our bionic hydrogen battery, we show how it can look in practice. In bionics, we are used to being inspired by nature and learning from it. And when it comes to energy efficiency, there is no other creature on this planet that is as bad at saving energy as we humans are. If we now bring together technology with bacteria, we can use and enhance their capabilities. So we are no longer just learning from nature, but now can collaborate with it to achieve greater goals. The protagonist in this project, as mentioned earlier, lives deep in a lake in Central Africa. In Lake Kivu, deep in the sediment, far away from light or oxygen. The name of this bacterium is Thermoanerobacter kivui. Professor Volker Müller at the University of Frankfurt and his team have been researching this exciting bacterium for years. Together, we have developed the bionic hydrogen battery. Here you can see how it works. In the first step, we produce hydrogen using water and energy in this electrolyzer. We put the hydrogen into the bioreactor here, together with CO2. And the bacteria cultivated convert these gases to formic acid. The formic acid accumulated in the bioreactor must now be extracted and then stored in this vessel. All the energy is now contained in this liquid and can be transported or stored over longer distances. If we want to release this energy, which is now stored here in the formic acid, at another location or at another time, we feed it to these bacteria in the bioreactor, in which the same bacteria are cultivated. There it is decomposed again into CO2 and hydrogen. We use the hydrogen released here in the fuel cell to convert it into electrical energy. No matter where, finally efficient. This process is not only efficient, but also safe. Here we use the wild type. Genetic manipulation is not necessary. As you can see from the name, the strain is anaerobic. This means that it grows exclusively in the absence of oxygen. This has two advantages. Firstly, in the event of a leak, the strain dies immediately outside the reactor. There is no risk to humans. The process is designed in such a way that only the smallest amounts of hydrogen are present in the system at any given time. The cells are thermophilic, which means they grow best at 66 degrees Celsius. Another advantage is that growth comes to a complete standstill at low temperatures. This means that the cells can be stored in this state for several years and reactivated on demand at any time. This gives us many options for process control. On-demand retrieval is possible, as is continuous operation. Compared to established processes, we have the advantage of mild temperatures and low pressures at a maximum of 1.5 bar. Although it is a biological process, the reaction takes place very quickly, as we use these cells as a catalyst, which means that they are not used up in the actual process. And with sufficient regeneration phases, it is possible to continue this process indefinitely. And that is our contribution to hydrogen as the energy carrier of the future.